Welcome back to the series on the Rigol MSO5000 and embedded systems. What you see on the screen is what is often called a burst, that is a train of pulses. And what may be difficult to see, and I'll try to point to it with the mouse pointer, is there is a very tiny glitch over here to the right. What we're going to talk about today are the basic triggers of the MSO5000, and the trigger that I'm using is the edge trigger. In fact, this is basically just what happens when you hit the auto key, that is the auto set button. You get a trace like this, and then if you simply expand out by changing the time base and move the trigger over to the left, you get something like this. I'll turn this menu off. Let me move the trigger over a little bit further. But there is a tiny anomaly there, and we'd like to look at that in a little more detail. And that's where a second basic trigger comes into mind. Now, with the edge trigger, the two main things to remember are you have to make sure that you have the trigger level, which can be found in the front panel section labeled trigger. It is the control in that trigger section, and notice the yellow line, dotted line that goes across. You need to have this set. Now, if you happen to have it set up here, there is no way you would catch that little anomaly anyway. But assuming that you have it set for about the middle, the question then becomes, how do you catch that little glitch? And we'll talk about that next. But a second thing you need to be aware of is the hold-off time needs to be appropriately set. Now, the hold-off time is in the trigger menu, and I'm just going to click on the T right here to bring up the trigger menu. It is down in this area, and right now it's set to 16 nanoseconds, which I think is the default. It can go down to 8 nanoseconds, and it can go up to, I don't know, a huge amount, maybe 8-10 seconds. I don't know what the top is, but way more than you'll ever need. Notice that it's also set for DC coupling with rising slope, and it's an edge trigger on channel 1. Now that is the configuration that the scope uses when you do an auto set. So let's now change this type from edge to pulse. Now I've already set up the pulse settings, which I'll show you in a minute. But now notice the trigger is still over here on the left, but now we're triggering on that little pulse. So let's move back to about the same position we were in. Now the rest of the waveform is still there, and we are triggering reliably on that pulse. We can now look at that pulse in some detail. Let's move the trigger back to the center and go to 20 nanoseconds per division, and you see that pulse is a little less than 40 nanoseconds. If we let's move the trigger over there and then move the trigger level down. Now you see it begins here a little more than 40 nanoseconds before the beginning, and it's back down to 10% at the midpoint. So it's about a 40 nanosecond pulse. Now let's look at how we have the pulse trigger set. Notice that it says it's a pulse type. We're still on channel 1. We're still positive going. But then in the when it says less than. And in the next box it says 50 nanoseconds. So it's saying any pulse narrower than 50 nanoseconds. And that's exactly what we've got. Notice the hold off is still 16 nanoseconds. And we have a reliable trigger on the this narrow glitch, this narrow pulse. That is the pulse trigger mode. So, just so we understand where we are. We started out with an edge trigger, which is what the auto set did for us. And by the way, edge trigger is the way that oscilloscopes used to always trigger. That used to be the only way. It was only when digital oscilloscopes began to appear that it was economically feasible to put in all of these other trigger modes. So one of the first trigger modes that was put in was the pulse trigger. And I think that was done by Tektronix, and I think it was done in the 1980s. It was a big advantage because it allowed you to trigger on narrow pulses or wide pulses. Suppose you only wanted to trigger on a wide pulse. Let me set that up. Now I've changed the time base a little bit, and notice that we now have 500 nanoseconds per division. Notice that all of these pulses are less than a division wide except this one. This one pulse is a little over 500 nanoseconds. So let's go into the pulse trigger menu and let's set to greater than 500 nanoseconds. And you notice now, let me move it back to the left a little bit. Now the trigger is on this wide pulse. So what we've seen is that the pulse trigger allows us to decide how wide a pulse we want to trigger on. It can be a wide pulse, in which case we use the greater than. It can be a narrow pulse, like this little artifact here, or it might be one of these. So the pulse trigger augments the edge trigger in many ways. It makes up for some of the deficiencies. Like I say, this is one of the basic triggers. I now have a signal from the PSG 9080, the unit made by Juntech that I looked at recently. And what it is generating is an 80% duty cycle ramp at a frequency of 10 kilohertz. You notice that the trigger is set up to the slope trigger, once again on channel 1, and it's set up for a rising slope that is greater than 50 nanoseconds. And there are levels that are set. Level A is set about the 90% point and level B about the 10% point. We'll look at those in just a second. But now what I'm going to do is I'm going to go from 80% duty cycle to 90%. And notice the waveform now locks in. And that's because the slope now from the 10% point, which is about here, to the 90% point about here, is now in excess of 50 microseconds. Notice here 50 microseconds. Now let's look at the levels so you get a feel. There's level A, and that's this top line, and level B is the lower line. And notice we have them, they're probably set to about 85% right now, but the actual levels don't matter in a case like this where the slope is linear. But the idea is that the slope of this signal, let me increase the time base a little bit there so you can get an idea. This is now 20 microseconds per division. So from this point to that point is about, let's see, 20, 40, 60, 80, a little over 90 microseconds from the lowest point to the highest. But from the 15% to the 85% point is definitely more than 50, because this is 20, 40, 60. So I'm going to go back down on the duty cycle to 80% again. And notice that the waveform becomes unstable, because now the slope is tilted higher and is no longer greater than the amount that I have set in the slope window. Once again, we'll go back to 90%, and you see it locks in. This is what the slope trigger is used for. When you are looking for, or you want to separate out parts of a waveform that have a particular slope. Now, we could have set this to less than and had a falling edge and triggered on, for example, this side. Or we might want to only look at times when the rise is, the slope is much steeper. The idea is that you set two levels, a level A at the top and a level B at the bottom. You then set the amount of time that has to elapse, or that is the critical time, between when the waveform crosses the lower level, that is B, and the upper level, or if you have it in the other, in other words, instead of rising, if you have falling, it's the time that it passes from level A down through level B. At any rate, that amount of time has to meet the criteria for the amount set in the, in this case, it's 50 microseconds. So this is how the slope trigger works. Now let's finish this video by taking a look at, quite frankly, a bit of an antiquated signal. We're going to look at an NTSC, that is a National Technical Standards Committee, just call it old television, video signal. So now we have a video signal on the MSO5000. Now, this particular video signal is an NDSC, that is the old, what some people now call analog television standard. I'm not going to try to go into a lot of detail on this particular signal, but what you see here is the sync pulse, that is the horizontal sync pulse. This is the signal that tells the television that you should be at the far right edge of the screen, and you should be retracing to the left. In other words, if this were the TV screen, the spot is over here, and it is rapidly moving back to the left, ready to start another scan line. So, as you probably recall, the way that television works, at least before digital, was there was a spot on a cathode ray tube which would slowly sweep across the screen, putting alternate lighter or darker areas from the picture. When it reached the far right edge of the screen, as you see it from the viewer's perspective, it would then quickly move back to the left, called retrace. And this pulse is the pulse that triggers the retrace. Now, there is also, as it's doing that is going from left to right, it's also moving from top to bottom. So it traces a line at the top, then it moves down a little and traces a line below that, and keeps doing that until it gets to the bottom of the screen, traces the last, and then when it retraces from this point, it doesn't retrace to the left side over here. Instead, it retraces back up to the upper left-hand corner up here in the screen. And I'll show you what that looks like by moving this trace over a little bit to the left. I have it set up so that this is the video. When the video reaches the end of this frame or field, the time from this point to this point is the time it takes that spot to move from the lower right-hand corner to the upper left-hand corner, ready for the next line of video. And that's this interval. This is called the vertical sync pulse, and it is broken up into pieces. Normally this would just be one big pulse, but it is broken up into segments called equalizing pulses. For technical reasons that I won't get into, it has to do with keeping the horizontal oscillator synced during the vertical retrace time and so on, but we won't get into much of that detail. At any rate, this is the video trigger. And one reason that I'm showing the video trigger is there also is the capability to do a number of different standards. Notice that I have it set to NTSC over here. Let me go back to that. I accidentally touched the touch screen. But notice that it can also do PAL, phased alternate line, and CCAM, sequential. The PAL is used in Europe, and CCAM is, I think, used in Asia. These are other standards. The old US standard was NTSC. You can do everything from 480 progressive at 60 Hertz all the way up to 1080 progressive at 30 Hertz. You also can do 1080p 50, 1080p 60, and so on. So those are the more modern standards. I'm not going to try to show you those. I have a generator that will generate those signals, but it's stored in an inconvenient location, let me put it that way. So I thought I would like to close this segment on basic triggering of the MSO5000 with the video trigger, in part because it's an unusual signal that you don't normally see. But the modern standard, that is the digital television standard, is to some extent based on the old NTSC. At least it uses the same basic format. In other words, the pixels are still put on the screen from left to right, top to bottom, just as they were in the old days. Well, I hope you've enjoyed this video and gotten a little bit out of it. The triggering is going to be something that we're going to come back to again and again as we look at how you debug a system. In other words, how do you find out if the system is working? That is, it doesn't contain any anomalies. And if it does contain anomalies, how do you find them and figure out why those are appearing and get rid of them. So, as I say, triggering will come back to haunt us many times through this video sequence. But in the meantime, I'd like you to stay safe, have some fun, get in the lab, and have a nice day.